ladies and gentlemen, my name is Brian McLogan, and in this lesson, I'm going to work through my notes on piecewise functions. So this is another lesson that I provided to my students, and I just want to basically get the answers, so therefore I can provide them to them. And I figured, well, let's just do another installment of me working through my lesson and recording that for all of you guys out there. So first way, just to kind of explain through my lesson, the first thing I did is I just kind of started sketching X and Y graphs. So basically what I'm doing is I'm going to give students a scenario and have them graph it. So the first one, and again, I wrote these myself. So the the punctuation and everything else might not be exact, and I do apologize to all of my English teachers, for that. But so it says a pot of boiling water at room temperature is placed on a stove. The pot is then heated to boiling. It takes 5 minutes for the water to boil. The water is left at boiling for 10 minutes before the stove is turned off. The pot is left to cool for 30 minutes before being removed from the stove. Graph the temperature of the pot based on the time it was on the stove. So the kind of point of this is, not for students to get this graph correct, but just for them to kind of like understand the relationship of, a word problem as well as, what that graph would look like. So for instance, let's just say this is going to be the temp. I'll put the temp on this axis and the time on this axis, right? So basically we have from 0 to 5, it's being heated up. Now, again, rather than going into, what is all these temperatures and all this kind of stuff, Celsius, Fahrenheit, I'm just gonna say here's room temperature, there's boiling. So from 0 to 5, it increases, right? And then for the next, 10 minutes, it's on the stove, is left boiling. So that's gonna be, at 15, it's gonna remain constant, right? And that's something we talked about in characteristics of functions. And then it's turned off and cooled for another 30 more minutes. So that's going to be all the way over here, let's say to 45. And, some of the question is, does it go completely back to room temperature? For those of you that are a little bit more familiar here, realize that it's not going to get exactly probably to room temperature. Might be a little bit warmer. We could also talk about the curves of the cooling effect and all that kind of stuff. But really, my idea was just to make sure students got something like this. But understanding, again, going through that understanding of functions, that time is the independent variable here and temperature is your dependent variable. It's going to depend on the time of, the temperature depends on when the boiling pot is on the stove. Then we looked at another situation. A price plan for the cell phone data has 3 options based on how much data you use. For each amount of the data you use up to 4 gigabytes, but not including within a month, you'll be charged $20 per gigabyte. And if you use between 4 gigabytes and 8 gigabytes, not including 8 gigabytes, then you'll be charged a flat fee of $100. And for data, you are charged $100. And for unlimited data, you are charged $170 per gigabyte. So we have that from there up to 4 gigabytes, but not including. So that again, but that not including. So anything that you use from 0 to 4 gigabytes, not including 4 gigabytes, though, you're going to be charged $20 per gigabyte. So sketch a graph on how much it costs based on the amount of data used within a month. So again, we're looking for this relationship, right? We have this input and this output. And what we want to do is we can see, well, what's going to be the independent variable? The independent variable is going to be how much data you use. And the output is going to be your cost. How much is going to, cost you to use so much data? So we basically have 2 intervals here. We have 0 to 4. We have 4 to 8. And then we're going to have unlimited after that. Anything over 8 is basically unlimited. You can use however much you want. So from 0 to 4, we have this what we call a direct relationship. For every gigabyte you use, you're going to be charged. So if you use 1 gigabyte, you're charged $20. 2 gigabytes, $40. And so that's basically like graphing the line, 20x. Y is equal to 20x. So it's going to represent a line. Let's just kind of go, the height then would be 80. But the important thing here is you're never going to get to 80, right? Because it's not including 80. So if you spend 3.99 gigabytes, you're going to get charged. But if once you spend $4, 4 gigabytes, you automatically get moved up to the next plan. All right. And the next plan then is just going to be a flat fee for $100. So let's put $100 up here. And then from 100, that's going to be from 4 to 8 gigabytes. But again, once you use 8 gigabytes, they're going to say, hey, you know what, congratulations, you're now up to the next plan. So now you can use as much data as you want to. So if you use 7.9 gigabytes, you're going to pay $100. Once you use 8 gigabytes, though, you go up to the unlimited plan, which is going to look something like that. Okay. And then the last one here is a restaurant wants to help raise funds for a charity. They decide to match what you spend within the restaurant as a donation to the charity. They also provide a family special, which if purchased at $40, they will donate $50. That's not right. Yeah, that's right. Okay, yeah. So sketch a graph that represents the donations of the restaurant. So I had to, I thought about this one on my own end. So I had to, kind of explain this one to the students. I was thinking of, the way I was thinking about this is whatever, if you go to the restaurant, whatever you spend, the restaurant's going to donate, right? But they have this special meal that costs $40. It's like a family meal, right? And sometimes you go to restaurants, they have the family platters, buy the whole family platter. So if I go there by myself, I don't want to spend a family platter. Maybe I just want to get a sandwich or whatever. There's no need for me to buy a family platter. Obviously, though, if I take my family there, it would make sense for me to go and purchase the family platter. And I think I actually meant for that to be $100. Well, let's just leave it at $50. So if I purchase it at $40, then they're going to donate basically an extra $10. So everything else is a dollar for dollar. Whatever you spend, they match it, right? Whatever you spend, they match it. So it's that equal relationship. So again, we need to determine what should be the independent variable, what should be the dependent variable. So the independent variable in this case is going to be how much money you spend. And then this is going to be how much money they donate, right? So again, everything kind of works out here as once we get into the, what was I thinking? Oh, so, if they spend, if you spend $5, get something cheap, then they're going to donate $5, right? However, at $40, they're not going to donate. Well, the key thing is students what if I spend $40 without, buying the family meal? And I say, that's just not possible. Okay. There's no way you can spend $40 without getting the family meal. So the only way that this works is the only way for you to spend exactly $40 is to buy the family meal, which costs $40, but then they will not donate $40. They're going to donate $50. Right. So you can see how that kind of works. All right. So again, I just basically wanted my students just to kind of get used to looking at these graphs, kind of seeing what these graphs look like, and kind of see how they're related and how they're different from what they did. So we had a little discussion, what is something that all these graphs have in common? How are they different? How are these graphs different than the previously studied 12 basic functions? And the basic thing that I wanted students to come away from this is, one, these are all functions, right? They all pass the vertical line test. The other thing is this is discontinuous. That's discontinuous, but that's continuous. So they're not all the same, right? But I think the main thing that you can see is, one, they really do represent a real world situation fairly well. So the important thing about the, representing that real world situation is, a lot of times when we're just dealing with one function, that's not really a great situation. That's not really a great model to represent something that's happening in real life. But by using a combination of different types of functions, we can represent things, I think, a little bit more accurately, and just something that's going to make a little bit more sense in the context of a, situation. And the other thing you could also say is all the x and the y's are all positive. It doesn't really make sense to be talking about negative, values in this case. So I think that's something very important to students to recognize. And then I thought there was something else I was going to talk about. I can't. But basically, you can see that all combining them is what is good. So that's kind of our discussion here. And then from there, we just kind of get into, well, all right, so let's go ahead and take a break here and get, let's kind of now pivot. So we learned about this. Well, actually, sorry, one thing. These are all what we call piecewise functions. Actually, I did put them. These are piecewise. They're basically a combination of more functions. So we're going to talk, that's obviously the name of this lesson is piecewise functions. So that's why it's okay, I can talk about it. But before we actually get into the definition and examples of piecewise functions, let's again start with some things that we feel a little bit more comfortable with, starting with graphing line. So in this case, we have a line that's in slope-intercept form, y equals mx plus b. And from back in the day, hopefully you remember that b represents the y-intercept and m represents the slope. In this case, we have the slope represented as a fraction. And so therefore, we can just kind of remember that's the rise over the run. I don't want to get too much into the graphing the lines. Hopefully that's something you remember. Here, this y-intercept here is going to be -1 on the y-axis, and that's going to tell us to rise 1, 2, 3 over 2 units. All we need is really 2 units to go ahead and write the graph. And there's one thing that, like, when I was teaching graphing lines, and I'm not sure how your teacher was, but, you know, we always included like those arrows. Like that means that graph is going to extend. And that was really important because I think in this case, if you recognize this, you know, this is the domain is negative infinity to infinity. And the range is negative infinity to infinity. And I think this is very important because when we talked about the transformations of the functions, you know, last chapter, whatever we did to this function, it didn't really matter. The domain range was always going to be the same. However, if we restrict this domain, like what actually happens? And that's what we're going to discuss in these next couple of examples. So, next couple example says graph the following functions based on the domain restriction, and then determine the domain range of and any discontinuity. So discontinuity being a hole, a asymptote, or a jump discontinuity. And actually, that doesn't really make sense for. That's not for this one. Actually, I need to change that. Just talk about the domain range. We're not going to look at discontinuities here. That's for another one. Sorry. Actually, well, no. I guess we could. Yeah, never mind. I'll keep that there. But anyways, so what we're going to do is we're going to graph the exact same line, but now we're going to restrict that line for different discontinuities. You can see, or different domain restrictions. So instead of the domain and the range being from negative infinity to infinity, we are now going to restrict the domain and kind of see what the new range is going to be. Because it's kind of, this is like the domain restriction. Like for instance, when we get to this for example, we have y equals 3/2 x minus 1. So we're only going to graph this for x values from negative infinity to 0. So I already know, like, the graph looks like this, right? 1, 2, 3 over 2. So the graph looks from here, and the graph looks like there, right? We already know that's what the graph looks like. Don't worry about the exact points, but hopefully you understand the perfect points. But the issue here is, again, this is only true for my domain restriction is negative infinity to 0. So therefore, anything to the right of this is not going to be included. Now, it's very important because a lot of students, what I saw them do was only eliminate everything to the right of 0 for the y value. But again, these are domain restrictions. So this is the x value that we are restricting. Now, hopefully I can do this correctly. Perfect. And again, that's an open, that's a parenthesis, so that's going to be an open circle. Now, our domain is, obviously you can see our domain restricted. And not only is our domain restricted, by restricting our domain, we actually just restricted the range. Now, there's no discontinuities. You can see there's a hole, but again, that's not a hole that breaks up the domain of the function, right? It doesn't break up, like you can still graph this function, you know, without, you know, jumping over, you know, any holes or jumps or anything like that. So it's still a function. This is not a discontinuity when a hole is at the endpoint. But we do have a change in our range. So my domain is obviously going to be my domain restriction. That's easy. But my range now is going to be, again, negative infinity to 0. Okay. Now, they don't always match up. But in this case, you can see that they do, and that's kind of nice. All right, so the next one here is y equals 3/2 x minus 1. So again, we have our negative 1 y-intercept. We're going to go up 3, 1, 2, 3, over 2. And just a reminder, we could also go down 3, right? 3/2 is equal to negative 3 over negative 2. So we could also go down 3, 1, 2, 3, to the left 2. So we could do that line, or we could do that line. But either way, if you go in the positive or the negative direction, you can see that they both fall in the same line. However, our graph, though, is only defined from negative 2 to positive 2. So I messed up here. That's only going to be from negative 2 all the way to positive 2. Now, hopefully my eraser will work all right here, and I can delete. There you go, and delete that one. There you go. So now you can see that I graphed the line, but it's not true to, like, extending. It's only true from negative 2 to 2. Therefore, this graph is undefined there and there. So let's see. That's going to be at, that's negative 2. So my domain here is negative 2, obviously to 2. But my range is, you can see how low this graph goes, right? It goes down to actually negative 4, undefined, all the way up to 2, defined. All right, Let's get on to the next one is 3 half x minus 1. That's going to be all values from 0 to infinity. Hopefully you kind of get the pattern here. Rather than graphing the whole line, I could also just say, well, it's going to be included at 0. Again, x is equal to 0, not the y coordinate, the x coordinate, because this is domain restrictions. And then, oops, 0 is cross at -1. And then we're going to go up 3 over 2. And there you go. So my domain here is going to be, again, 0 to 2. And my range is now going to be from -1 to infinity. And again, for each one of these, we have not had discontinuity because for each one of these, our graph has not been broken up. However, in this next example, we get something a little bit more special. So I have 3 half x minus 1, but x cannot equal 0. It's kind of interesting. So I have the same graph. It's just my x coordinate cannot equal 0. So therefore, I'm just going to use an open circle. So I'm still going to go up 1, 2, 1, 2, 3 over 2. Down 3 over 2. Either way you want to look at it, like it's fine. The thing is, the graph just does not equal 0. So you can see there's a hole. This is the one value now that we have a discontinuity because it breaks up my graph as far as graphing it continuously. So my domain is going to be all real numbers except for 0. So I can write that like this. My range is going to be the same, except it's all real numbers except for -1. Like that. So let's get that rid of it. And then let's go ahead and label the discontinuity. So we're going to say a hole at x equals 0. So you can see when x equals 0, you can see that the graph is undefined. All right. So the main important thing is I wanted to show you like you can graph any function and you can actually restrict the domain. So at least that's how it works for lines. And that was hopefully, idea I wanted to bring to my students is as far as making everything easy. And then we kind of had a little discussion, as far as identifying the domain restriction. Just because the domain and range are equal as far as all real numbers for the parent graph, that doesn't mean that once we restrict the domain of the function that the range is going to be restricted in the same way, right? You can see through all these functions, once I restrict the domain and range are no longer the same. This one it is, this one it's not, right? Also, these are the same, these are not. So it's no longer that case. So you just got to really understand what the graph would look like to better understand how those domain restrictions happen. And so, but I started with lines just to help kind of students really get a good feel of what we're doing with domain restrictions. And then I went into, well, last class period we did transformations of functions. So let's go ahead and practice, graphing some of those functions. So in the next one, we're going to graph the following equations and then determine the domain and range on the restriction. So I am going to do this based off of that you have an understanding of what the parent graph looks like, as well as what the transformations are, as well as what the domain and range would be of these parent graphs. And if that's something that you're not there yet, that's fine. Just make sure that you go back and reference the graphs and the domain and range, as well as the transformations, so you can kind of follow along. So in this case, we have a quadratic. I know that's like the U-shaped graph. I can see here that I have a reflection about the y-axis, and I have a vertical shift down 1. So I can see that this graph is going to go down here. So rather than drawing the graph, looks something like that. Now again, I know my graph is not perfect, and I'm not trying to be perfect with my graph. What I told my students, as long as you have the general shape, that's where we're kind of working at. Like that's fine. But this is only going to be true for x values that are less than or equal to 0. So that's going to be all values to the left of the y-axis. So that means I'm just going to delete everything to the right of the y-axis. And again, assuming you're working with a pencil, this is something you can easily do. The next one probably is going to take a little math for a couple students to really understand. We have y equals, let's rearrange these, -x plus 1. However, we recognize we have a b and a c, so therefore we're going to factor out that. Now we can recognize we have a reflection about the y-axis, which fortunately for the v-shaped graph, just like the quadratic, or the absolute value, I'm sorry, is symmetrical about the y-axis, so it doesn't really actually impact the graph. The only thing that's really happening is we're shifting this graph 1 unit to the right. Now this does have a relationship of up 1 over 1, just like a quadratic, even though I didn't get that really well. Okay, so you do reflect it about the y-axis first, and then you would shift it to the right one. And this is only true for x values that are greater than 1. So that's kind of interesting. So therefore, everything over here is not going to work. Let's see, that little dot is done. Actually, let's get rid of that. And now, let's just do a nice big open circle there. Oh, I forgot to go back and do the domain and range. Jeez. So here, previously for a quadratic, we know the domain is all real numbers, right? There's no problem with plugging in any number in for x, squaring it, and subtracting 1. However, it's saying it's only true for x values that are less than or equal to 0. So now I'm using my domain restrictions as an inequality. So we need to understand what the interval notation would be. So that would be from negative infinity to 0. And the range, we're going to look at the graph here. We can see that's going to be from negative infinity to negative 1. All right, in the next example here, we can see the domain is going to be x is greater than 1. So to write that in interval notation is going to be 1 to infinity, as well as my range now is going to be 0 to infinity. There we go. All right, then we worked on just, we still got some more graphing lines. Now we got the square root function. This is going to be the square root function, and therefore we're going to be shifting it left 2, up 3. So I'm going to take this graph to left 2 and then up 3. Hopefully you know what this graph looks like, the general shape. That's all I've really been asking students. And then we know this is only going to be true, though, from negative 2 is less than or less than or equal to 2. So you can kind of see like where my graph kind of follows here. There's negative 2, and there's 2. So anything outside of those two graphs, right, I can just go ahead and delete. So, boom. Oops, no, I want that. I wanted to get, I'm an idiot. That I only want between negative 2 and 2. Okay, so my graph is not going to be perfect, right? Because we all recognize that we're not going to be perfect. But hopefully you recognize, you have that square root graph, but it's restricted between negative 2 and 2, where negative 2 is undefined, so I use an open circle, and 2 is defined. Let's go ahead and work from here, the domain and range. Did I talk about discontinuity? I kind of forgot. No, just the discontinuity. Okay, so therefore, I'm going to have my domain here is going to be from negative 2, open circle, to positive 2, included. And then my range here is, now how am I going to figure out my range? Now this one's kind of interesting. This one might not be as obvious. I didn't really graph this as well. Well, let's figure out what the y values are. If I were to plug in negative 2 in for x, negative 2 plus 2 is 0. Square root of 0 is 0. 0 plus 3 is 3. 3 is defined. So I'll have 3. And then, actually that's an undefined point, sorry. And then if I were to plug in 2, 2 plus 2 is 4, square root of 4 is 2, 2 plus 3 is 5. And that is defined, okay? So what you can do is you can plug in those values, and that's exactly what I did. I plugged in negative 2 to give me 3, and I plugged in y sub 2 to give me 5. Right? Because remember, the range is the output of the function. So it's very important if your graph is something that you're maybe, not as familiar with, square root function or any other function you deal with. Remember, you can always plug it in to be able to figure out what those y values are. All right, last but not least, we have y equals x minus 3 cubed minus 2. All right, so that's the S-curve graph, the cubic graph, being shifted 3 units to the right and down 2. Okay. Now, however, I notice at 3, so remember the S-curve graph looks like this, has an x-intercept, shift 3. That's going to be an open circle there. And then the graph's going to look something like that. Now, based on this graph, I can recognize that the domain is going to be all real numbers except for 3. Just put it a little bit farther down. And the range is going to be all real numbers except for negative 2. Okay. All right, so not only can we apply transformations to lines, we can apply transformations to regular functions. And then I kind of had a little discussion with students, like how does how is graphing based on those domain restrictions? When graphing a function, how can we determine if and what we are graphing is correct? And again, that kind of goes back to what we did with this graph. Like, you might not follow me on this cubic function, right? But you could plug in any number that you want to be able to find a point. And typically, you can plug in, the endpoints. Really, it says plug in any number you want to, or even plug in 3. Like, where should this hole be? I don't know. Plug in 3. 3 minus 3 is 0. 0 cubed is 0. Minus 2 is -2. And you can see that at 3, -2 is where the hole is. So you can plug in points to be able to verify. And that's what I really want to make sure students, kind of understood with this, especially with the square root or any other function that they may not be as familiar with. All right, but in reality, piecewise functions, something that we talked about, is not really just about doing domain restrictions on one function. It's really doing restrictions on multiple functions. So in this case, what we're going to have is graph the following function with the domain restrictions on the same graph, then determine the domain, range, and the type of discontinuity. All right, so now we are dealing with one function, another function, and then different domain restrictions. So we're going to see how that affects them, as well as really kind of refining what type of restrictions, discontinuities that is going to provide us. All right, so let's go ahead and get this over with. Here on the graph two functions with the restriction. So first equation is y equals -2/3 x plus 2, only for x values greater than 3. So I'm going to have plus 2. And then I'm going to have down 2. So down 2 over 3. Now again, this is only for x values that are less than that, right? So therefore I'm going to leave that as an open circle. And I'm just going to kind of go back that way. Then I have x minus 3, so that's going to be down 3 here. And again, remember, you can think of this as like, -3 up 1 over 1, up 1 over 1, up 1 over 1, right? And then x minus 3 is greater or equal to 3. So that would be up 1 over 1. Supposed to go through that graph. And there you can see it. It kind of looks like the V-shaped graph. It's not perfect, right? But you can see that actually this graph actually fills in that open circle, and then makes the graph actually continuous. So even though it is two different functions, it's actually a continuous function, which is kind of interesting. So my domain here is all real numbers. My range is from 0 to infinity, and it is continuous. All right, the next one here is y equals continuous, whatever. So the next one is basically the exact same graph here, but now some things are, I think we're going maybe in the other direction here. So I have -2/3 plus 2, so plus 2, -2 over 3. But that's going to be for x values greater than 3, so I'm going to go open circle, and I'm going to continue this graph down 2 over 3, so whatever, it's going to go that direction. And then I have x minus 3, so x minus 3, same graph, but it's going to be an open circle, but it's going to be less than 3. So let's actually kind of follow that graph again. There you go. Okay, so you can see they still connect at the exact same point here. The difference is, though, since this is not greater than or less than or equal to, you can see that's going to be an open circle. So my domain is not going to be all real numbers anymore. It's going to be -infinity to 3, union 3 to infinity. My range is going to be -infinity to 0, not including 0. And you can see that I'm going to have a hole at x equals 3. Because again, you can see that the hole breaks apart that function. All right, next one is graph two functions with restrictions again. So we have the exact same functions again. Now we have -3. Now we can see, though, our restrictions are actually changing at 0, which is kind of a little interesting. Up here, they were changing at 3. Now they're changing at 0. So let's see how that kind of impacts. So we have plus 2, negative 2/3, so it's going to be less than 0. So that means it's going to be to the left. So instead of going down and to the right, I'm going to go up and to the left. So I'm going to go from 2, so I'm going to go up 2 to left 3. So 2, 3. And that's less than or equal to. So I'm going to fill in that dot at 0. X minus 3, so down to negative 3. And that's going to be greater than 0, so it's going to be open circle. Let's just do up 1 and actually let's do that up 1 and over 1, right? Well, that'd be up 2 and over 2. Yeah, let's just do up 2 and over 2. That's fine. Okay, so now you can see that this is going to be a jump discontinuity. So the domain is actually all real numbers, right? Because even though it's undefined here, it's defined there. So the domain is all real numbers. My range is only defined for values down from negative 3. So therefore, that's going to be negative 3 to infinity. And you can see that I have a jump at 0. So a jump at x is equal to 0. All right. That's it from there. All right, guys. Last one here for at least for this group. So we have negative 2/3 x plus 2 for x is greater than 0. So now we're going to do an open circle at 2, down 2, over 3. There's my graph. All right. And then we have x minus 3 for x is less than 0. So minus 3. And then let's see. Let's just go down 1, over 1. Okay. So this one looks very similar. The problem is, though, that my function is not defined at x is equal to 0. Well, again, that doesn't matter in terms of the discontinuity. You can still see this is a jump. However, that is going to impact my domain because now my domain is undefined at x is equal to 0. So my domain here is now going to be negative infinity to 0, union 0 to infinity. My range is going to be negative infinity. Since this goes down, that's actually pretty interesting. That's kind of important. Since this is going down here, this is going to define all values. So my domain is going to be from negative infinity all the way up to my highest value here, which is 2. And we can see that there is a jump at x is equal to 0. All right, so the purpose of kind of looking at these graphs was really kind of open up the discussion of what happens when we take 2 or more functions, with restrictions. Like what are some things that can happen? How does that impact the domain and range? Is it possible for us to graph, just 2 lines? Is it possible to graph more of them? More functions? Do we have to just restrict this to like lines? Could it be 2 or more functions? What happens when we start doing this? And you can see there are discontinuities that occur, but not always. Doesn't have to be. And that kind of goes back to our warm-up. Just because you're adding more and more functions doesn't mean there has to be a discontinuity. But you can see that where the lines connect is a very important issue. And that's something that we're going to talk about in this course, is where those two graphs combined. If they can be continuous, they could be a hole, they could be a jump, right? There's a lot of things that are going on there that we really need to make sure we understand. So that's why we kind of need to kind of bring in this into our discussion as far as what is, how can we describe these types of functions? And the way to describe these types of functions is basically a piecewise function. And a piecewise function is something that we've already kind of talked about. It's basically just a function that contains 2 or more functions with a domain restriction. And rather than writing them like this, we use our piecewise function notation, where we give the function a name and then we group each and every one of those equations or functions with their restrictions to the right. So I wrote this down as 3 functions with the restriction because in this class, the maximum number of functions and restrictions we'll be dealing with is 3. However, there really is no limit to how many functions and restrictions you can have. So that's just kind of one of those important things to note. So now hopefully, I've set up the process or the understanding of, piecewise functions. So therefore we can get into the process. Basically, we're just looking into graphing each function separately by applying the transformations to the parent graph, kind of like what we already did, and then go ahead and applying the restrictions or the domain restrictions to the graph by basically replacing the portions of the graph that are not defined by these domain restrictions. So it's really kind of the exact same process that we just already did. Really, the only difference is the notation is going to be kind of different. So here what we're going to do is we're just going to work on 6 different examples of graphing piecewise functions. And you can see that these are all different or unique in their own little way based on their transformations. Here we have 3 functions, and then we have different domain restrictions going on here. So what we're going to do is graph them, then we're going to describe the discontinuity of the graph. All right, so the first one, negative x. Now, rather than graphing the whole graph, since we've already kind of practiced that, I'm just going to go ahead and only graph it based on the domain restriction. So this is going to be x where it's greater than 0. So therefore, it's going to be an open circle. Negative x has a y-intercept here. And that's going to be going down here like that. And then we have 2x minus 3. That's going to be for x is less than 0. So I'm going to go down to negative 3. 1, 2, 3. That's going to again be an open circle, and let's see, that's going to be that'd be a positive slope, and it's going to be down to over 1. So let's see, the graph would look something like this. Okay, and we can say there is a jump at x is equal to 0. All right, in the next one, we have x squared minus 2. So therefore, that's a quadratic. That's going to negative 2. For x is only greater than 0. So therefore, we'll go over 1 up 1, over 2 up 4, 1, 2, 3, 4. Just in case I need to be a little bit issue with there. And then the next one is a absolute value here at negative 2. So now they have this negative on the inside, but remember guys, the negative on the inside is just a reflection about the y-axis, which is not going to impact my absolute value. In this case here, though, I have a 1/2 x, so that kind of changes my slope. So instead of it going up 1, or over 1 up 1, it's going to go over 2 up 2, because it's actually going to be a vertical compression. And that's going to be minus 2, so it's going to be shifted down 2. So it's going to look something like that. Again, not trying to be perfect here, but you can see by graphing this that I have a hole at x is equal to 0. All right, and also you should be available or should be aware or able to determine the domain and range just by graphing these as well. I'm not going to do that for these because that's just one thing I just want students just to kind of focus on the graphing portion, as we've already kind of practiced identifying the domain and range. So for this one, we need to graph these 2 functions. To graph this function, you might be easier just to look at this in terms of its transformations with b factored out. So therefore, we can see this is a reflection about the y-axis as well as being shifted 1 unit to the left. All right, that's going to be less than or equal to. And therefore, this graph is going to look something like this, right? Because the square root graph. And so it's basically being reflected and then shifting 1 unit to the left. And then this one is the cube root graph, which is that horizontal S-curve. It's also being shifted 1 unit to the left, but it's being reflected about the x-axis. So, here's the graph, right? And then, so if we reflect it about the y-axis, now the graph's going to look like that, being shifted 1 unit to the left. So I'd probably say it actually is going to look something kind of similar to like the square root graph, just kind of going in the other direction. But you can see here, there is no discontinuity. So actually, I'll just write continuous. The next one, m of x, is, so we have the reciprocal function. If you remember that as the hyperbola, you have horizontal axis, horizontal and vertical asymptotes, but it's being shifted 3 units to the right. So 1, 2, 3. So therefore, my vertical asymptote of the parent graph is at x equals 0. So now it's going to be at x equals 3. My horizontal asymptote was at y equals 0. So now it's going to be at y is equal to 1. So that's what my graph looks like. But basically, it says at 2, the graph is going to equal 4. So it does not, or whatever 2 is, the graph does not equal. So, let's just put an open circle there. Now, oops, but it's important, you got to know what the graph looks like, right? The graph is actually in the first as well as in the second quadrant. So let's just put 2, x cannot equal 2 here. Let's see, if I did a 2, that'd be some, I don't know, some fraction. But the graph looks like this. So it's important to make sure you know what the graph looks like. let's see, if I put that in, that'd be a negative. Yeah, it would be a positive value. All right, so again, roughly right there. But then it's equal to 4, so there's a defined value here. So in this one, we actually have two discontinuities. We have a hole at x equals 2, and we have a vertical asymptote that is a part of the restriction here of that. So we can say hole at x equals 2 and a asymptote at x equals 3. Okay. The next one, now we have 3 equations. So again, kind of the same thing. It's just, following each and every graph and just make sure restricted. So this first one, we have x squared where x is less than 0. So that's going to be an open circle over 2 up 4. Okay, so the graph is going to look something like that. Then we have 2, which again, if you're graphing that, y is equal to 2 is just a horizontal line, right? Y is always going to equal 2. And that's only true from 0 to 2. So 2 is right here. So it is open at 0, but it's included at 2. So it's just going to be a nice little horizontal line there. And then this one looks pretty kind of confusing, right? A lot of things going on, but it's this quadratic. It's the same as this parent graph, being shifted 2 units to the right, being shifted up 4, and then being reflected down. So it's an open circle, right? And then, but it's actually focusing down. So, wow, a lot of things going on. So here you can basically see there's 2 jumps. We have a jump at 0 and we have a jump at 2. At x equal to 0 and x is equal to 2. All right, for the last one here, I have p of x equals e to the x plus 1, negative x, and ln of x. So again, we have the same kind of opportunity. Here we have the exponential and the logarithmic, which a lot of students aren't as familiar with. So, but again, if you just look at the parent graphs, you see this is e to the x with a vertical shift of 1 unit to the left. The one point that we are familiar with the exponential graph is with no transformations would be 0, 1. So therefore, if I shift to 1 unit to left, my graph's going to look like that. And again, this is only true for values that are less than -1, so that's going to be an open circle. So even though, the graph would look like that, right, because it's an open circle, it's only true for values that are less than -1. So I am just going to erase that portion. Then the next one is my negative x, which is my negative identity function, open at -1, and then going all the way to +1, which is, again, open. So just kind of looks like that. And this next one is going to be ln of x, so it's just the parent function, which again continues here at this. Again, the parent function of ln of x has a x-intercept at 1, and therefore the graph would look something like this. But we're only going to graph it for values that are greater than 1, so therefore we're not going to graph this side. So now we can see that we have a hole at x equals -1, and we have a jump at x is equal to 1. All right. All right, and so the last thing I really wanted to come up with was looking into the evaluations. But actually, before we even get to that, let's kind of talk about one more last little discussion. So when we're looking at the discussion, the main thing that I want students to kind of look at is when you're graphing these, look at these these discontinuities and where do the discontinuities occur? If there is a discontinuity, where do they always occur? Well, the main important thing, there's 2 things that I want you to come away from this. First of all, notice that each of these functions is continuous. Continuous for all real numbers, continuous for all real numbers. So the only way that this is going to be a discontinuity is where we separate them based on these domain restrictions. And you can see we separate them at 0, right? And of course, that is where my discontinuity is. Again, domain all real numbers, domain all real numbers. So the only time this is going to have a discontinuity is at 0, because that's where we change from one function to the next. However, it's important that just because, in this case, here you have a domain restriction, right? This is for only values that are greater than 0, but based on the restrictions, now we have a domain from -infinity to -1. Here we have a domain of all real numbers, but this function is continuous. So you just don't want to assume that, oh, the domain is going to be a discontinuity at -1, because look they connect at -1, right? And sometimes they might not connect, in there at all. So you got to understand what the graph looks like. In the same regard, don't forget about domain restrictions of a function. So in this case, we can say that, oh, well, I have a hole at 2. Like, hopefully you understand, you see this and you say, oh, there's a hole at 2. But don't forget there's a vertical asymptote at 3. Like, that does not go away. You got to make sure you describe both of those. So that's something that's very important that I wanted you to see. And sometimes, you know, in the same case, you're not sure that's a hole and that's a hole. In this case, that's a jump and that's a jump. Here, sometimes it's a hole or it's a jump. So you got to be able to differentiate, you know, if they're going to meet at -1. We just don't want to, we could just say there's discontinuities at -1 and 1. But again, do they connect? Do they not connect? You know, are they a hole discontinuity or a jump discontinuity? So that's why the graphing portion, you know, is very helpful. So basically go ahead and describe the, you know, where the discontinuities occur. Okay. All right, and then the last piece, which, you know, one of the things I really wanted to drive home with students was the evaluating the piecewise functions, because this one gets students a lot. They get very confused on how to find the value of a function. And, you know, it's really not trying to trick you here. You know, if I have f of 3, right, we have, you know, that's going to be, let's do this again real quick. If I have f of x squared, what am I doing? You know, let's just call it f of x equals, you know, x squared plus 2. And if I say, what is f of 3? Well, then we just plug in 3 in for x, right? Fairly basic, you know, stuff. So that is equal to, so then we could say f of 11. Sorry, f of 3 is going to equal 11, right? All right, cool. But the problem is, if you're going to plug like j of 0, let's go and look at j of 0. Like if I'm going to figure out where j of 0 is, like just in the graph, which function do I plug this into, right? And hopefully you can recognize that nothing, forget about looking at the graph. We're just going to use the graph as a tool. But what if I just ask you to evaluate without knowing what the graph looks like? Then what you can recognize here is that when we're looking at this discontinuity, there's nothing that this function is defined for at 0. X is either greater than 0 or x is less than 0. So I can easily kind of go to this and just say it's undefined. And then when is j is -2? Now here's the important thing that I really want students to kind of look at. So a lot of students, I can't even tell you how many times this happens. It happens every year. We figure out what is j of 2. And people want to plug -2 into both equations. But again, if j of -2, and again, this chapter's name is functions, right? So for every input, you can only have one unique output. You can't plug in a number and get 2 different outputs. So it makes no sense for us to plug in -2 into both these equations and get 2 answers, right? That goes against everything that we've talked about as far as the definition of a function. So then which equation do we pick? Well, again, that all relies on the restrictions. This function is only true for x values that are greater than 0. You can see on the graph. This graph only is defined for positive values. This function is only defined for negative values. So of course, if I want to figure out what is -2, I need to plug it into this bottom equation. So therefore, what is that, 2x minus 3? So therefore, all I'm going to do to evaluate j of -2 is I'm just doing 2 times -2 minus 3. Crap, I keep on forgetting. I should have rewritten those down so I can see them. 2x minus 3. Yep. And so 2 times -2 is -4. Minus 3 is equal to -7. Okay? And let's just go and take a look at that and see if it kind of makes sense. Like, if you go to -2, yeah, it's going to be down there to -7. Like, that kind of makes sense. All right? All right. So now the next one, here again, forget about the whole. Let's just kind of see, what is that one? J, K. So K of 3 and K of 0. You know, let's just do that over here, and then I'll copy and paste it. That's probably easier. Okay, so K of 3 and K of 0. So again, K of 3 is which one is defined for 3? Well, obviously you could go to the graph 1, 2, 3 and like try to figure out where it is. Or you can say, well, which function is defined for positive values? You know, which 3 is, which would be this top equation. So we're just going to plug in 3 squared minus 2, which is 9 minus 2, which is 7. And then if I want to figure out what is K of 0, again, we recognize that nothing is defined at 0. That's a hole, right? There's no defined value for K of 0. So therefore, I'm just going to say undefined. So let's go ahead and see if I can copy this now. and kind of bring that down. Close. I'll try to get those a little bit closer to each other. All right, the next one is L of -1 and -3. Okay, so this one's kind of interesting, the L of -1 and L of -3. So when we have L of -1, actually I'll put it up here. I would give myself a little bit more room. L of -1, you can see that they're both defined at -1, or they both have a -1. So which one do we choose, right? Well, the difference here is when we're dealing with 0, they're greater than or less than. So in this case, you can see that this is less than or equal to. So I'm going to plug it into this top equation. So that's going to be square root of negative times a -1 minus 1. That's a lot of negatives going on there. So that's going to be a +1 minus 1, which is 0. So therefore, that's just going to give me 0. And then, oh, I was doing it on the top equation. Oh, that's good. We don't even know what the graph looks like. I'm not going to remember what the graph looks like, so that's fine. And then crap, was it 3? -3. And then if I want to do for -3, again, I'm going to use the same equation. So L of -3 is going to be -3 minus -3 is 3, minus 1 is 2. So therefore, I'm just going to leave that as the square root of 2. Yep, okay. So 3. Yeah, I can't remember what I was trying to do. So let's just go ahead and check that one out. Ah, crap. That's not going to work. Let's do that one. -3. Oh, let's look at the graph. Where's -1? You can see at -1, we're at 0. But at -3, we're going to be at some weird value that I'm not going to be sure of, right? So -1 is there. But if we're going to do L of -3, which is more left, then we'll have L of -3 is going to be a square root of a -3 minus 1. So minus -3 is going to be a +3, minus 1 is 2. So it's going to be some value, you know, and we'll just leave that as a radical. Can't simplify that any further. All right, M of 2 and M of 3. So let's go and look at the M of 2 and M of 3. So obviously, M cannot equal 2 here, right? But it can't equal 2 for that equation, but it can equal 2 here. So M of 2 is just equal to 4. And M of 3, we already know there's a vertical asymptote there, right? So that's going to be undefined. So that one was rather fun to solve. That one, I'll take that one all day. Just bring that down. Perfect. N of 2 and N of 1/3. Ooh, bringing in some fractions. All right, let's go and take a look at what that is. So we have N of 2 and N of 1/3. So N of 2, we got to figure out where that's going to be defined. And you can see here that I have the less than or equal to 2. So therefore, it's going to be exactly this equation. So at N of 2, I am going to be defined for that's equal to 2. And then N of 1/3. Well, so which function here is dealing with 1/3? Like which interval? When x is less than 0? No, 1/3 is positive. When x is greater than 2? No, 1/3 is less than 1. So again, you can see 1/3 falls within the restriction of 0 to 2. So therefore, that's also going to equal 2. And again, let's look at that. At 2, you can see the graph is defined at 2. At 1/3, you can see the graph is defined for at 1/3. So you can see how it makes sense, you know, just by looking at the graph as well, or at least hopefully. All right, and then the last one is our exponential. Let's go and look at that. So in this case, I have P of -1 and P of -1/2. All right, so again, we're looking at the -1, where you can see nothing is equal to -1, right? There's no value up there in the equation where that's equal to -1. And also, if you look at the graph, you can see there's a hole. So if I say P of -1, that is going to be undefined. That's a hole. And then P of 1/2, if you look on a 1/2, you can see it's defined, and it's going to be defined for this function. So that's going to be a -1/2. And you also can see that 1/2 falls between -1 and 1. All right, keep on having trouble getting that. Come on. There we go. All right. Perfect. All right, and then we basically just kind of wrapped up the lesson talking about, what is important when evaluating piecewise functions. I think the main thing is understanding where the discontinuities are. If you, are not asked to graph it, but having a general understanding what that graph looks like. However, as you kind of noticed, you can solve all of these without actually knowing what the graph looks like. You can just plug them in to the graph, but just make sure the main thing, do not plug them into both equations. That goes against the very definition of a function. So we definitely don't want to do that. And then, obviously understanding the graph. And that was basically how we ended up the lesson. And then I just asked students, to do a quick little reflection on what they understood from the graph or understood from the lesson, as well as, some things that they maybe are still kind of struggling. So I invite you to kind of share your thoughts and maybe some things that you were kind of having a hard time struggle from there. Again, this is a lesson that in slides that I went through in my class. And so we take, I will read through the comments and try to see, if there's anything else I can do to help you out with the function. So on to the next lesson. Cheers.